Hi, my name is Anjana Iyer, and this is Lab 3 Magnetic Field of a Bar Magnet. So, the purpose of this lab is to create a linearized graph of the magnetic field, which will be represented by the letter B and distance r, to get the magnetic dipole moment of the magnet. We also want to observe the changes in the magnetic field of the bar magnet when it's 45 degrees off axis. We also want to compare the off axis experimental magnetic field to a computationally obtained off axis field. In preview of the results, we got the mu value, or I got the mu value to be 0.955, and then the experimental off-axis value to be 5.88 times 10 to the negative 5 Teslas, and then the computational off-axis value to be 1.13 times 10 to the negative 5. In this lab, the main equations used were the Biot-Savart law and the distance dependence equation. The law shown above is an equation that gives the magnetic field produced due to a current carrying segment. It directly relates magnetic fields to currents, and the equation on the top left can be used in addition to the law of superposition, which states that the net magnetic field is a sum of the individual pieces. The distance dependency equation shown below, where B bar equals kr to the n, um, is represented where k is a magnetic constant and n is the value that we're going to determine. The initial conditions of this lab were B equals x 00 microteslas, and then the system was taken to be the bar magnet and the surroundings were everything else. I've attached a portion of my data at the bottom, and those values are for 20, 140, 260, 380, and 500 microteslas. So with that data, we created a graph, and then I have this equation right here where y equals negative 1.2663, x minus 13.406, and the n value was found to be the slope, which is negative 1.2663. In order to find mu, the distance dependence equation was used along with the on-axis magnetic field equation. On the right-hand side, certain variables and equations are defined. The y equation can be attained from the previous data on the previous slide, and the k value can be calculated by taking e to the n, so e to the negative 13.406, yielding 1.5 times 10 to the negative 6th. We can then plug in all these values into the equation, kr to the n, and we can solve for mu, and it's going to be 0.955. Some observations during the experiment: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And then, in order to complete the off axis portion of the lab, the magnetometer a certain distance I put the magnetometer a certain distance x and y away, and then found the bx, by, and bz to find the magnetic field. And here is the data for that. The distance perpendicular was where b net equals 100 microteslas, or 0.168 meters. And here's a little diagram. For the code, I defined my constants at first. I also defined r hat and inputted the equation for b, plugging everything in. And on the right-hand side, the code that's shown right here, this is all going to create several vectors. And then on here, the average distance in the off field can be seen, and using that, a vector can be created to where we can find the magnetic field of it. And the final computational model is shown here with the following measurements, where the magnetic field perpendicular is negative 9.55 times 10 to the negative 5 in the x-hat direction, and d is 0.238. And then we also have the magnetic field at 45 degrees, which is 3.56 times 10 to the negative 6 in the x-hat direction, and 1.07 in times 10 to the negative 5th in the y-hat direction. And then the net magnetic field at 45 degrees is also shown here. And in conclusion, the magnetic dipole moment was found to be 0.955, and then the experimental model yielded an off-axis magnetic field of 5.9 times 10 to the negative 5 teslas, and the computational model yielded an off-axis magnetic field of 1.1 times 10 to the negative 5. And some errors that could have occurred were the location of the magnetometer sensor may not have been completely precise, surrounding metals could have affected the magnetic field measurements, and fluctuations in the magnetic field measurements may have prevented accurate results. What if and why? For the what if part, the results would have been inaccurate, considering that the Earth's magnetic field would interfere with the bar's magnetic field. And for the second what if part, Um, if we were to stick two identical magnets together and run the experiment again, I think the magnitude would double, but the direction would likely stay the same.